Yo, step into class, y'all. Today we'll be talking about the software architecture of a serverless CRUD, whatever you want to call it, API. All right, and we'll be using AWS serverless services, API gateway, Lambda, DynamoDB, and then we'll be using an IAC infrastructure as code tool, not Terraform. But if you know Terraform, you get a thumbs up. Not CloudFormation, yuck. That's definitely not. You get a thumbs down for that. And then if you know CDK, you get a thumbs up for that. But we're not using any of those. We'll be using the Serverless Framework, okay, as IAC tool today. And we'll be incorporating all of this and deploying it to different branches with GitHub Actions, all right? So the first question though, right, I'm going to talk about all that stuff. The first question is, what the heck is an API? Well, first of all, API stands for Application Programming Interface. And that doesn't really necessarily make it any easier to understand, right? But I'm going to explain it. Basically, an API is an interface. This is an API, right? The API sits between two systems, okay? This system here, and then we have a system here. They don't know anything about each other. They don't communicate with each other. This person who sits in the middle is the API that translates from the front to the back, whatever, right? This system usually sends a request to the API to say, hey, I want you to do something for me, okay? I don't know how all the process is working in the background, but I need you to take that request, send it to the back end of your system, let them process it, and then let them send me back a response. Once they send back a response, the API is responsible for sending it back to the system. Okay, so this sits in the middle for these two people to communicate, but they don't know anything about each other. All right, this sends a request, this processes a request, and sends a response back, and the API sits in the middle. So I'm gonna give you an example of, let's say there's a coffee shop, right? And I go to the coffee shop, and I don't know, people are some big coffee drinkers. I'm not. I drink hot chocolate. So if I go to the coffee shop, I'm gonna order hot chocolate. Okay, I tell the waiter, I tell the cashier that, yo, I want a hot chocolate. Order the hot chocolate. The cashier takes my order, sends it to the back, sends my request of an order to the back, all right? The back is the person who's actually making it, okay? I don't know anything about them. I don't really care how they're making the hot chocolate. I don't know the processes of cup, drink, or this amount of sugar, blah. I don't know, and I don't care. Send my order to the back, let them process it, and then they're gonna respond back. What do they respond back with? With my hot chocolate, okay? So the person in the back making it is gonna respond back to the cashier. This person doesn't come to me. This person goes back to the cashier and gives them my order, my hot chocolate order. And then the waiter, the API, is like, okay, I got your hot chocolate. Gives it to me. That's how APIs work. The waiter, the cashier, is the interface, the API in the middle, because I'm interfacing with the API. I'm interfacing with the waiter or cashier, whatever you want to call it. I don't know what's happening in the background, but the waiter, the cashier, is responsible for taking my request of an order to the back, let that person process it. They're going to give the order back to the cashier, and the cashier gives me the stuff. That is how APIs work. We talked about earlier CRUD or CRUD. What the heck is CRUD and CRUD or blah, blah, blah. Now these systems, right? We're talking about systems. Communicating actually over the internet. The way how we communicate over the internet is using HTTP or HTTPS. This is the protocol that enables communication over the internet. Now, for each action, right? A system can make multiple actions. Like I want to do multiple things. If I'm the customer, I'm going to the waiter or cashier. There are a couple of things I can do, right? I can make an order. I can ask for the menu. After I made an order, I can ask them, hey, can I view my order to make sure that's the right thing I got? So I can create an order. I can ask for my order back so I can view it, and I can update my order. Okay, I don't just want hot chocolate. I want croissants too. Add that to my order. And then I can also delete my order, meaning, yo, I don't want it anymore for, I don't know, any reason. I don't want my hot chocolate anymore. I'm running late. I got to cut. So I can create an order. I can read my order, get my order and read it and make sure it's correct. I can update my order, and I can also delete my order. That's where CRUD comes from. CRUD, whatever. So this system, when it comes to HTTP, we have actions, right? That you can use HTTP to make actions, make requests to the API. And these actions are, all right, C for create. These arrow back and forth is because you send a request, the API takes the request, processes it, and then they send back the response, and then the API sends a response back to you. So there's create. There's also read. I don't know why I use caps lock here. But the next one is update. Okay? And the last one is delete. All right. Now for these 4 actions, when it comes to HTTP, there's something called methods that correlate directly to each of these actions, right? That basically tells the API what action you want to do. And with HTTP, these methods, pay attention to the word, methods are to create, you make a post request. For read, you make a get request. For update, you make a put request. For delete, you make a delete request. Delete, whatever. Okay? So this system, through the protocol of HTTP, is going to make a request. The type of request, the method that is being sent to the API is going to know what action this system wants to do. So if this system sends a HTTP GET request, it means that they want to read their order, right? They want to get their order so I can see the information. If they send a POST request, it means they want to create an order, create. If they send a PUT request, they want to update their order. If they send a delete HTTP request, they want to delete their order, all right? So we're talking about coffee and restaurants or whatever right now, right? So now let's use an actual scenario to this entire system design talk, right? And cloud computing concepts that we're talking about. We have Alex. Alex has an online coffee shop, right? Just stay with me. And she doesn't have a building, but she actually allows people to make orders online. And then they come and pick it up at a specific place, but it's not a building where you come and sit and dine in, right? So that means that her core business is ran on this application or website. So she has a website that is an online coffee shop, okay? She also has an API. She uses an API for people to make requests to the coffee shop's API, all right? These requests will be either post, get, put, delete for whatever they want to do with their order, okay? So Alex is like, all right, since this coffee online shop, whatever, is going to be my main source of business and revenue, this is the thing that's going to drive people to actually come and actually get business from, I need to find the cheapest way to do this, all right? Well, I can buy my own physical servers and host this thing on my servers in my house, but that's a lot of freaking money. But I heard about this thing called the cloud. The cloud, where I can borrow or use resources over the internet from other huge organizations who can lend it to me. And I only pay for what I use. So the cloud will allow me to actually use compute resources, networking resources, storage resources, as long as I have access to the internet in a pay-as-you-go model. So I only pay for what I use, right? So I don't have to have my own physical server in my house. Like, that's horrible. Like, that's a lot of money. And plus, if I needed to scale out pretty quickly, I would have to buy more servers to scale my operations. Like, if my coffee shop gets popular, well, I don't have the money for that. I don't have the budget for that. I don't want to manage that. So guess what I'm going to do? I'm going to use AWS, and I am going to use something called EC2, which is a virtual machine. Okay, virtual machine, you pay as you go. You only pay for this compute system, this compute service that's actually going to power. It's going to be the engine in the back end that's going to process, that's going to allow us to process that business logic, right? Whenever the post or get or put or delete comes in and it goes to the back end, this thing is going to be processed We need some type of compute power engine, and we're going to use, Alex decides to use EC2, Elastic Cloud Compute. Sorry, Elastic Compute Cloud. I said it backwards. Okay, so this engine is going to process stuff. So this is an EC2. Think EC2. Once the information gets in there, right, we have a create. Okay, create. C for create. R for read. U for update. And D for delete, right? These come to the EC2, and the EC2 has to process this. All right, so once it processes it, guess what? Those orders, they have to be tracked, right? And stored somewhere. Where do you store this? Well, on something called a database. Okay? And with AWS, I don't know, we're going to be using maybe RDS. RDS, Relational Database Service, is a managed database service on AWS, right? Okay, so we're going to be using RDS. Don't focus too much on the name. Just focus on what's happening, right? So this thing is the compute power that is going to process the information. We also have our code here. Our code is going to process each one of these different types of requests. It's going to be on the EC2. And then the EC2 is going to be responsible for storing, saving that information, making writes or reads. This stands for write or reads to the database. So I'm going to be writing. Writing means I'm going to be putting the information inside a database. Reading, it means I'm going to get information from it, read information, all right? So this is how it works. Now, this is what we call a 3-tier architecture. Okay? Why do you think it's 3-tier? I'm trying to take a guess. Well, because we have 3 layers here, right? So this API would be considered the frontier, right? Frontier is what the user actually interacts with. This is the front end, right? This is the presentation layer or presentation tier, right? We also call this the front end. Now the middle, this is called the application tier. This is what processes the business logic. With these 4 API actions that's coming in, it has to be processed inside here first, right? So in here, this is actually called the application layer or application tier, also called back end. Right? This is the back end. This is the front end. What is this? Database. Easy, right? This is the database tier or layer, whatever you want to call it. Okay, cool. So this is Alex's infrastructure right now, right? The reason why this is good, 3-tier architecture, because it separates different operations, right? It separates concerns. So over here, we're interacting with the user. Over here, we're processing business logic. Over here, we're saving all our stuff in the database and interacting with the database. Now, imagine if all of this was inside one system. How tough would that be to manage that, right? That's rough, right? So it's better to separate different operations, huge operations that's going to be taking place in this entire system, right? So this is more modular, right? It separates each part. And because it separates each part, guess what we can do? We can actually scale each individual part independently. So if this EC2 instance, if there's a bunch of requests coming in, guess what happens? There's going to be too much load in this EC2 instance. We can actually scale just this part because this is getting a bunch of requests. This can stay the same. And then if this is getting too much writes and reads in our database, we can also scale this separately. So we can take care of each area separately because of the 3-tier architecture. And then because of security, right, we also increase security because each layer can be secured many different ways, right? We can add extra security here. Imagine if you had to secure this entire system inside one server, right? That's extremely tough and extremely hard. And in the real world, actually, big organizations, they have full teams that literally would only work on APIs. So dividing this, you can actually have a separate teams that work on different parts of the 3-tier architecture. You can have one team that literally only work on the code that is on the EC2 instance, on the virtual server that is going to actually process all these requests. We can have database administrators, database engineers, whatever, that literally only work on data, the data part of this entire system, okay? Now, going back to our example of Alex's coffee shop, right? Online coffee shop. Her shop begins to get popular. So she starts getting a bunch of create, read, update, delete requests. Bunch, right? We're thinking thousands or whatever, right? And initially, she didn't have a bunch of requests. So she only used one EC2 instance for an online coffee shop. But now that she's getting so many requests, there's too much load on the EC2 instance. And guess what happens? Guess what's the risk? If this EC2 instance was to get too much load, it can crash. And if this crashes, guess what happens? The entire system is down. Why? Because this is what you call a single point of failure. It's not highly available. Highly available means that you eliminate single points of failure. It means that if something was to break, if there is a fault, you can still be able to operate, right? Because you have some type of backup, you've created some type of mechanism to allow you to either come up pretty quickly from an issue or from a fault, or you have mechanisms to take care of if something was to go down, we have something else in the backup to keep this system running. That's highly available. But with this, you have a single point of failure, so it's not a highly available system. Now, Alex is like, well, I need to increase this, right? How do I increase this? Well, there's a word called scaling. Scaling has to do with increasing or decreasing the amount of capacity you have based off of the demands. So if more demands come, we need to be able to scale this EC2 instance, this one EC2 instance, to maybe 4, maybe 5, maybe 10, based off of the surge of requests coming in. And then once a request goes down for any reason, we also be able to scale down, right? So that has to do with scaling, right? Scaling mechanisms. She thought about using EC2 Autoscaling on AWS, which automatically scales the EC2 instance. So they're in a group, right? Say we have a minimum of 1 EC2 instance, and then you set the maximum of maybe 4 or 5 EC2 instances. And it's going to scale within the minimum and the maximum based off of the traffic that is coming in, right? There's a specific metric that is being tracked, whether it's the CPU utilization is being tracked. And once the CPU utilization goes up too high, we can scale out, right? That is the EC2 Autoscaling on AWS. Now, we're still using EC2s, okay? And maybe she's trying to think ahead, right? Way ahead. Okay, well, I'm still using EC2s, but guess what the issue about EC2s? EC2s, you pay as you go, right? That's the cloud. But when there isn't a request, yes, there's a bunch of requests happening, but every split second, 4 seconds, 10 seconds, 20 seconds, there is not a request coming in, the EC2 instance is still running. She's still paying for the instance that is still running, even when there's no request coming in, okay? And you may be like, oh, that's only 10 seconds, that's only 20 seconds. But after a month or 2 months, that's 10 seconds, 20 seconds, or how much seconds is in a day, right? You add that up, that's how much money that she's spending running this EC2 instance constantly, okay? So right now she's thinking, okay, there's a couple of issues, right? I need to be able to scale rapidly. I need to be able to save money and not waste money whenever there's no request coming in, right? So she wants to do that. And she also doesn't want to take care of the EC2 itself, the underlying compute, right? Because the EC2 is a virtual server. You still have to manage the server itself, right? Different updates, right? Patching that has to be happening on the EC2 system itself, right? You have to manage the underlying system and still have her code running on top of this system that basically processes these different requests. So with all that stuff, she doesn't want to manage infrastructure. She wants to be able to scale rapidly. I'm talking like thousands of requests. And she also wants to be able to scale and be able to scale quickly for the many different requests that are coming in. She also doesn't want to manage infrastructure. She just wants to be able to focus on her code, right? She wants to write the code to process this and then forget about the infrastructure management. And then everything can just automatically scale quickly for her, without using an auto-scaling group, because auto-scaling group, it scales, but it still scales pretty slowly. We need something with like, boom, spawning thousands of instances of that compute power in like seconds, right? EC2 instance can do that, but it is pretty slow, okay? So that's where we move into the concept of serverless. What is serverless? Well, serverless is a concept, or what I call it, is a technology where cloud platforms, they say, we're going to manage the infrastructure for you. All we're going to do is give you a platform where you just put your code in and run it. You don't have to manage the underlying infrastructure. And then plus, we're also going to give you the ability to scale to thousands of instances of that compute. So meaning that whenever a request comes in and it's a lot, scale out quickly, scale back down. And you know what's the crazy part about it? We don't keep the compute running. Meaning for every second there is a request, that's when the compute is provisioned. Whenever that request is done and we don't need it anymore, it disappears. So if we're having some point where there might be a split second where there isn't requests coming in, when that happens, you can save costs on that because we won't have to spin up an instance of the serverless compute, okay? In AWS, there is a specific serverless service called, and I'm gonna go and show you, Lambda. This is what we're going to be doing. Lambda. It is a serverless compute service that you don't have to manage any of the, and it can spin up so many instances in split seconds, scale crazily to run your code for you. You just put your code in there and it just automatically runs whenever it's being invoked, right? That's the word. You invoked a Lambda function. So in this one Lambda function we're using, we are saying this Lambda function is going to, we have our code that's going to process, create, read, update, and delete, right? Lambda code. But the thing about Lambda code, it's only going to run or be triggered or be invoked whenever there's an actual request. Whenever there's no request, we save money, right? Nothing is happening. And it also can scale insanely. Plus, you don't have to worry about managing the infrastructure, okay? Now, we're talking about serverless, right? Well, if we're using Lambda here as a serverless, we might as well use the other components serverless because they give us the same benefits. Well, on AWS, there is a serverless database called, well, I guess I can draw it back. DynamoDB. Same benefits as what Lambda is. Scale insanely. Definitely good for distributed computing, distributed data. So we have DynamoDB, serverless service, serverless database service, okay? Has the same benefits as a Lambda and some other stuff too, right? But it's a serverless, no SQL, non-relational database on AWS, right? So we took out RDS and we put in DynamoDB and we're using Lambda. So both these are serverless. So we're taking the benefits of serverless and we are changing our infrastructure to be serverless. But guess what? We can also change the API to be serverless. Because on AWS, oh, my thing dropped. There is something called API Gateway. API Gateway is a serverless API Gateway is a serverless service that allows us to create APIs. So this service here is going to create an API for this system, and whenever there's a post, get, put, delete that's going to hit the system, this API is going to be responsible for sending that request to the Lambda function. The Lambda function, depending on how the request is going to be invoked and it's going to be rapidly scale out however it needs, and it only runs when it's needed. And then it's going to also write information and read information from a serverless DynamoDB service. So this is a serverless API, CRUD API, CRUD API, CRUD, all right? Now, But this right here, just the Lambda function, right, is going to be taken care of. Create, read, update, delete. We call this monolith. Monolith, right? This is the monolithic architecture for the compute, for the part that processes these, right? Why is this monolith? Mono stands for one, right? One, uno, whatever. Because on this Lambda function, we have all the code in one code base, in one place that takes care of create, read, update, delete. All those processes being done in one code base. That's called a monolith. Now there's what the positive side of monolith is, it's simple, right? If you don't have to scale crazily, you can use it, right? Because it's small and simple and it's manageable. But once it starts to grow, think about when you have to make changes to different parts of the code, right? All the parts are interdependent on each other, right? If there's an error in the code that only manages the delete, guess what? The entire Lambda function goes down. So if a developer is working on the delete function of the Lambda, just the delete, but then they mess up and there's an error, right? So delete is not working because create, read, update, all of that is inside one code base. If this messes up, everything else goes down because this is inoperable. This is not working anymore just because there's an error in the code that processes delete request. So that takes down create, read, update. Everything is down, right? Because we have this one, almost like a single point of failure, right? It's not highly available, even though each of these can, scale out to take on each of the requests. But if developer is messing up and they have errors in the code itself, if they take out one service, they take out all the other services. So what do we have to do? Right? What we're going to do is remove this. So what do we want to do? We want to move from a monolith architecture to, this is monolith, right? We're going to move from monolithical, whatever you call it, to microservice architecture. So if you put that together, micro means small, service means services. So smaller services, yes, that's what we're going to do. Instead of having one huge Lambda, guess what we're going to have? We're going to separate each of these services to be taken and being processed by separate Lambda functions. Okay? So create is on a separate Lambda function. Read is on a separate Lambda function. Update is on a separate Lambda function. Delete is on a separate Lambda function. You know what's crazy about this? Because we separate each service, now, if something was to happen to the delete service, right? Say delete service is not working for some reason. Boom. We can still process, create operations, read operations, and update operations because we've separated into different microservices. Each service has been separated to individual. And you know what's good about this? Now this can scale itself. This can work out itself. This can scale separately. This can scale separately. So let's say we have 100 creates and maybe only 2 deletes, right? This only needs 2 invocations, 1, 2. This hundreds, right? But guess what? If this was in one big one, the whole thing would have to scale 102 times. Like that one Lambda would have to scale, 102 invocations. But separating them, we can actually see that each process, each action can only focus on how much invocations that it needs, right? So separating them is pretty crazy. Again, in huge organizations, you can have literally an entire team that is only working on the service of create. This is all they work on, this Lambda function here. All day, every day, making this better, trying to improve on the processes just on this. So you can have separate teams working on separate services. They operate different outside of each other, right? This is cool. So this is a microservice architecture, okay? And then of course, each one of these are also going to read and write to the DynamoDB. All right, so I haven't talked about all of this. If you were to create this, right, an API with API gateway for Lambda functions in the application, back end to process these actions, and then DynamoDB. If you did it in the management console on AWS, click ops, what we call it, use your mouse and you go around and you click, 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 and then you create all this stuff. That's cool, right? But suppose you work at a big organization, you have all of this, and say you want to be able to repeatedly deploy this same thing over and over into multiple accounts, multiple environments, right? Or let's just say for some reason, this whole thing went down. Everything got deleted. All these resources got deleted. What would you do? You have to go back into the management console and start clicking and clicking and creating the entire thing again? Well, no. That's where infrastructure as code comes from. Infrastructure as code is defining your resources into a file, into a couple files, right? And this file is going to be the template whenever you want to deploy this entire infrastructure. So I can use configuration files, what we call it, and that sets the standard, right? So define all of this into one configuration file as code, okay? So you define everything here as code, and this becomes your source of truth. So whenever you want to deploy this entire thing again in a different environment, you just take that file, you move it to that environment, and you deploy this whole thing again automatically within minutes. Okay, so that's the power that you get from infrastructure as code. Let me give you an example, right, of infrastructure as code. Let's say we have a construction manager, whatever, and they are making an apartment complex. And all these apartment complexes are identical. Okay, so it makes the first one, makes the second one, makes the third one. How is the construction manager being able to replicate the same apartment complex over and over? Take a guess. The architectural diagram. An architect draws the diagram, right, that defines how the apartments are supposed to be made. And they go back to the architectural diagram and they, as a template to create or deploy an apartment complex, right, in this place. Then they'll deploy it again in this place. Then deploy it again in this place. They're literally just going back to the architectural diagram of that building. So that's what this is. This file is defining the entire infrastructure as code into one file. The system or whatever tool you're using, whether it's Terraform, blah, 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 is able to read the code, understand it, and then be able to automatically deploy on your behalf this entire infrastructure. And the infrastructure as code tool we'll be using is called, for this entire thing, Serverless Framework. This is an infrastructure as code tool specifically for serverless solutions, serverless resources that we create. So we talk about API gateway, Lambda, and DynamoDB, all that serverless. So serverless framework is specifically made for automatically deploying these types of services, okay? Now, with serverless framework, which I literally just learned last week, serverless framework uses CloudFormation underneath, which is horrible for me. Sorry for you AWS people, but the serverless framework creates an abstraction on top of CloudFormation, right? So when you deploy with serverless framework in your CLI, which is what you use, your command line interface, it's going to create some CloudFormation stacks, and CloudFormation is going to deploy it for you. Now, the issue with me for that is that, yes, this will work, but when you have issues like the template, the stack has an issue that it can't delete, or there's something wrong with the stack, you guys know troubleshooting CloudFormation errors is horrible. So if you have issues with the serverless framework deploying, and then you go into your AWS console and you see CloudFormation has some issue, you should have some type of background and understanding of CloudFormation to troubleshoot that. And if you don't, it's kind of tough, right? So you can't just rely on serverless framework. You still have to know how to understand what is deploying, the CloudFormation, right? So This thing deploys this entire thing using code in a configuration file. Now we're going to talk about something else called CI/CD. Remember I said that different developers work on these different lambdas, these different services, right? Processed inside each of these lambdas. So they're writing code in their local environment on their computer. Boom, boom, they're writing code, whatever. And let's just say that they write code and then they deploy it straight here. Boom, they deploy it and there's an issue, there's an error. It takes down the delete, right? Or let's just say multiple people are working on the same file at the same time, on the same service at the same time. One person deploys and the other person deploys. Well, how do you keep track of who's deploying what, Somebody can be working on the same service as the other person. How do we sync up and work together? How do we, that's a huge issue. Well, there's something called CI, the first part of CI/CD, which is continuous integration. Continuous integration allows multiple teams, multiple developers to work together on the same code base. Why? Because it creates, well, I won't get too deep into that. What it allows people to work together on the same code base. And then it also allows you to automatically run tests on that code. Okay? So before it even ever gets to production, when they write the code and it gets merged, what we call it, merged, tests will automatically run. Once those tests run, if there is an error, that crap is now going into production. Go back and go and fix that. Before it even gets close to production, we can test out the code and we can check the validity. We can check if there's any errors, whatever, right? So that's CI. That's continuous integration, okay? Now, after continuous integration, we might need to deploy, right? Automatically deploy. You can use, serverless framework. You can deploy it yourself in the CLI, right? Serverless, blah, 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 and deploy. Okay. Now let's just say we have 30 engineers and each of them is running serverless deploy. Somebody works on some type of code and says, hey, go run serverless deploy for me. You're going to run serverless deploy. Another person works on code, go and work serverless deploy for me. Then you keep doing that. That gets repetitive. That gets horrible. We need to be able to automate the deployment of new code being made and being generated, right? New code that actually passes the test, that wants to go straight into production, that is good to go into production. We need to be able to automatically deploy that. So there's something called continuous delivery, continuous deployment. So that's CI, we're at CD now, okay? So the fact is that CD, continuous deployment, continuous delivery, is just being able to automate the code from the time that is being merged, the time that is being tested, and once it passed that test, to automatically tell Serverless Framework, go and deploy all of this for me, okay? We automate that entire thing. So we use something called GitHub Actions, right? GitHub Actions, the crazy thing about GitHub Actions and other CI/CD solutions, that it gives us the possibility to automatically deploy all of this. And the other thing that it does is you can deploy to multiple environments. So you can use a GitHub Actions CI/CD pipeline to deploy to the development environment. And then also production environment, right? These are different environments. Why would you want different environments? Well, when we're developing, we want to test our things out. So if we want to test, we want to deploy to our deployment environment, which we can run multiple tests on. Once it works there, there's also another one. You can have stage environment. So stage and environment, which is like the second stage before it even moves production. So there's multiple stages, multiple places we can test different stuff before we move into production, okay? So this entire thing is what I've been building this weekend, okay? So I created a serverless CRUD application using these services, API Gateway, Lambda, DynamoDB, and then I use Serverless Framework that's going to automatically deploy this for me in my AWS account. But then I use GitHub Actions to be able to, whenever I'm writing code, I need to make changes to my code, I can just make the changes and then I can push them. And then once I get pushed in the pipeline, the GitHub Actions pipeline will automatically deploy to different stages for me. Okay, whether it's development stage or production, it'll do all this for me. So, I mean, That's it. Hope this kind of makes sense to you, because, you know, a lot of times that I'm going through this by myself, and this is how I go through it in my head, okay, when I'm trying to explain these things. But yeah, see y'all later.